Hey guys, it's Mr. C here, and I just want to start this video out by saying if you hear some scuffing in the background, that's my bearded dragon. She's running around in her cage right now. But anyway, in this video, what I'd like to do is illustrate an example dealing with the exponential law. It says here the formula A of t equals 165 times e, and in its power is 0.039 times t. And that function right there models the population of a particular city in thousands T years after 1998. And the big money question here is how long will it take for the population of the city to double? What I'd like to do is form a little laundry list off to the side. There are four major components um, that make up the exponential law function um, as it relates to this example. For instance, A of t, we actually do have a particular value of that buried into the language here. Specifically, um, it wants to know when will the population of the city double. So this is the key word here that actually provides us a particular value of A of t. But before I pen that down, I think we should maybe examine the value of A sub 0. A sub 0 is the initial amount, and A sub 0 is going to be the value that goes in front of the exponential expression. And so A sub 0 is 165. Now, that interprets as 165,000. So now that we know that the initial value, or A sub 0 is 165, we just double that to get the particular value of A of t. And doubling 165 gives us 330. We do also have a value of k that's in the power of e right in front of the variable t. I'd like to point that out. Our value of k is 0.039. Now notice that the value of k is greater than 0. So since the value of k is greater than 0, or in other words, positive, we are working with an uninhibited growth scenario in this problem. If you converted the value of k to a percent, it works out to be 3.9%. And the idea there is that as each year goes on, the population of the city increases by 3.9%. Of course, the fourth component is going to be the value of t, and that's a big IDK because it's the point of the problem. What you're going to do here is substitute all these numbers into the formula that's provided in the problem. I'm going to write 165 e to the 0.039 t on the left-hand side, and I'm going to set that expression equal to the value of A sub 0 once it's doubled, in other words, 330. And it throws us in an exponential equation setting. And so we're going to go ahead and solve this exponential equation. First thing we want to do is isolate the exponential. In other words, let's divide 165 to each side. We get e to the 0.039 t equaling 2. That 2 right there is representative of the fact that we want the population of the city to double. Now what we want to do is apply a log loop to get the exponential expression's exponent back down on the ground. So what I'll do here is start with the base e, wrap it around the 2 on the right-hand side, and finish off in the power of e. And this will allow us to rewrite this equation as follows. The natural log of 2 equals 0.039 t. Now all that is a one-liner right there. In other words, 0.039 t is back on the ground. That's no longer an exponent, just an ordinary algebraic expression there. And of course, what we do from here on out is divide each side by 0.039, and that isolates our variable t. So I'll write it this way: t equals the natural log of 2 all over 0.039. Now, for all practical reasons, you want to go ahead and type this into your graphing calculator. And if you round to the nearest year, it's going to take the population 18 years to double, okay, under the conditions that the initial um, population is 165,000, along with the fact that the growth rate is 0.039 or 3.9%. Now, if you're wondering what year that lands us in, adding 18 to 1998 puts us in 2016. All right, that's it for this video. Please let me know if you have any questions. Otherwise, thanks again for watching. I'll see you in the next one.